Hey everyone, so this last video is going to be focusing on our last gas law, which is the ideal gas law. As the name implies, this is when gases are acting in ideal behavior, so referring back to the kinetic molecular theory. And what's nice about the ideal gas law is basically all the previous gas laws we had discussed, there were certain conditions that were needing to be held constant. And so with the ideal gas law, they don't. So the ideal gas law reads PV equals nRT, but if you're a true chemistry pro, you actually refer to this as PivNert. It's a real thing. The variables in here apply. The P is pressure, the V is volume, the N is moles. Why did we have a new letter? I don't know, but moles is N. R is a constant, I'll talk more about that here in a bit, and then the T is temperature. So just to do some kind of basic review here really quick. Pressure can be measured in an assortment of amount of variables. It can be measured in ATM, it can be measured in kPa, it can be measured in millimeters of mercury, just to name a few. Volume for PivNert specifically has to be in liters. The constant I'm about to show you, this is R value here in just a little bit. You'll see why that's important here shortly. Moles is moles. It's not really a unit, right? It's just a count about the number of particles we've got. And as you should know by now, temperature always needs to be measured in Kelvin. All right. So here's where the constant thing kind of comes into play. I'm going to come back to this here in just a second. R is constant. It is basically just a number. There are a lot of equations. There's a lot of things where constants are used and applied. For example, pi is a constant, 3.14. So whenever pi is in an equation, you always plug in 3.14. Another one is E equals mc squared, Einstein's famous equation, if you've seen this before. The letter C in the equation actually stands for the speed of light, which measures to be 3.0 times 10 to the 8th meters per second. So whenever you see a letter C in an equation, it always is standing for the speed of light. So then we plug in that number. That's how R works in the ideal gas law. So it's just letting us know we need to plug in a number, a constant, in order to make these relationships true. Here's what's weird though. So temperature is always Kelvin, moles is always moles, volume is always liters. But pressure has so many different variables to it, and there really isn't a standard unit of pressure that's consistently used. So for example, you might recall you could have 1 atmosphere, and that's equivalent to 101.3 kilopascals, and then that's equal to 760 millimeters of mercury. So you kind of run into an issue when you're using PivNert, where if you plugged in 1 atmosphere, and then another person plugged in 760 millimeters of mercury, you're going to get different answers. So because pressure can change, R, the constant, has to change to reflect what unit of pressure is being used in order to still make all of these relationships true. And that's exactly what happens down here. We have 3 different R value constants, 0.0821, 8.314, and 62.4. So these are the different numbers that we can plug in for R. We plug in the different numbers based on what unit of pressure is being measured, whether it be ATM, kilopascals, or millimeters of mercury. If we plug in 1 atmosphere, or however many atmospheres, it doesn't have to be 1, we plug in this number, kilopascals this number, millimeters of mercury this number. So these are constant values that you need to be able to know and use in order to use PivNert. So let's go ahead and try one. So basically PivNert is useful when you know some conditions of a gas and not others. So for example, what pressure in kilopascals is exerted by 1.5 moles of hydrogen gas in a 0.300 liter container at 310 Kelvin? So if we want to identify our variables here really quick first, P is pressure, that's what we're trying to solve for, but it specifically wants it in kilopascals, so I'm going to write that down. V is volume, so that was 0.300 liters. N, remember, is moles, so 1.5 moles. R is a constant, and it's going to be one of these 3 numbers here, and we're going to pick the number based on the unit of pressure. So since pressure wanted to be kilopascals, I'm going to pick the R value that matches with that, so kilopascals. So I'm going to pick 8.3 0.314 liters times kilopascals over moles times Kelvin. This big thing I just wrote down right here is the unit of R. So you know how I wrote like 0.300 liters and 1.5 moles? That's R's unit, that big icky thing. You'll see how that plays out here in just a second. T is temperature, and that for this problem was 310 Kelvin. Okay, so these are all my variables. So now that I've got these, I'm going to go ahead and plug in and solve. So I'm going to rearrange this first, actually. And just kidding, no, I'm not. All right, so I'm looking for P, looking for pressure. My V is volume. N is moles, and so that was 1.5. R was 8.314, and I'm going to write that whole unit down here really quick so you can see how that plays out. And then my temperature was 310 Kelvin. Okay, so here's me plugging in all of my work. So I wanted to solve for P, I wanted to solve for pressure. So I'm going to go ahead and divide by 0.300 liters on both sides here to make that cancel out. And I want you to watch what happens. So remember, when anything that's the same on the top and the bottom, you can cancel out. So if I'm looking here, I've got moles here and here. This moles, the one right here, this is the one that's coming from that R unit. I've got liters here and here. I've got Kelvin here and here. And so as far as units go, everything cancels out except for kilopascals. And what I wanted to solve for was pressure in kilopascals. So when you have that gigantic R unit, that allows for all of the units to cancel out except for the one that you're looking for. And that's why we use that. So if I go ahead and solve now, I'm going to do 1.5 times 8.314 times 310 divided by 0.300. Sig figs. Looks like I've got 2 here, 2 there, so it looks like I'm going to go for 2. I'm getting 13,000 kPa for my final answer. All right. That's basically it as far as Pivner goes, is you know some conditions of a gas, you don't know the other conditions, and you're going to plug in the variables and solve. So why don't you go ahead and try this one on your own, and then and pause the video here, and then tune back in once you've given this one a shot. All right. So your final answer here should be 10 Kelvin. So our pressure was 1.2 atmospheres, volume 2.5 liters, moles 3.5 moles, and the R you should have picked is this 0.0821. Why? Because the pressure was measured in ATM, so you should pick the R that was affiliated with ATM, with atmospheres. When you go ahead and plug in here, this should be what you're typing into your calculator at the end. All of your units cancel out except for Kelvin, and that's what we're trying to solve for, and that's why your answer is 10 Kelvin. What do you think? 10 Kelvin, hot or cold? Cold. Remember, 0 Kelvin is the temperature that is absolute zero, and that is the temperature in which all particles stop moving. So if this truly were a gas at these conditions, it would be very, 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 very chilly. So, fun fact, since Pivnert has moles, has N in it, now that we can solve for moles with Pivnert, we can basically do all the other stuff we've ever done with moles before. Stoichiometry, yay! If you solve for moles, you can go ahead and throw moles and do anything else we've done up until this point. So let's try it. Here's a problem. Pretend there's an arrow here. Cool. How many liters of hydrogen gas are needed to react completely with 725 grams of tungsten oxide if the room is 23 degrees Celsius and at a pressure of 744 millimeters of mercury? Lots of information here, but basically we're just kind of combining the two worlds of stoichiometry and then the ideal gas law. Here's what I like to do just to kind of like breathe for a second and figure out what I've got. So I've got grams here, okay? And I know I can convert grams to moles because stoichiometry. I have a temperature here. I have a pressure here. and it's asking me for how many liters, and I know that's a volume. All right, so I've got PT in moles if I convert it from grams, and I want volume. Pivnert is PV equals nRT. I've got P, I've got T, I can figure out N, it wants V, R is a constant. I've got everything I need. So the first thing I'm going to need to do here is convert these grams to moles. So let's go ahead and come down here and do that. So I've got 725 grams of tungsten oxide. And I can convert grams of tungsten oxide to moles of tungsten oxide. And here's where we're going to really quickly read this through one more time. How many liters of hydrogen gas are needed to react completely with 725 grams of tungsten oxide? So I want liters of hydrogen. Okay. Well, if I want liters of hydrogen, if I stopped right here, I would have moles of tungsten oxide. So if I plugged that into Pivnert, if I plugged in moles of tungsten oxide, I would be solving for volume of tungsten oxide. But I want volume of hydrogen. So what I can do is I can set up one more step, and I can convert the moles of tungsten oxide to moles of hydrogen. And then I can Pivnert it up. One quick thing. Usually I have a lot of students ask me, why can't I just go straight from moles of hydrogen to liters of hydrogen using 22.4, because that's how many liters are at STP. Well, you got to ask yourself, is that STP? 23 degrees Celsius and 744 millimeters of mercury? No. So since the conditions aren't STP, we cannot use our magical 22.4 liter number, which is a bummer. So let's go ahead and get this. So we need the molar mass of tungsten oxide. So just as a review, you would find tungsten, I found you, 183.85, and then I would add that up with 3 oxygens. So 183.85. 183.85 plus 16 times 3. I'm getting 231.85 grams in 1 mole. And then remember, for the ratio, we look to the coefficients for that. So it looks like this is a 1 to 3 ratio. So a 1 to 3 ratio. So I'll go ahead and solve for that. So 725 divided by 231.85 times 3, it looks like I get 3 sig figs, 9.38 moles of hydrogen. All right, that's the stoich part. Now what I can do with that is I can move on to the Pivnert part. So the Pivnert part of this is going to be, my pressure was 744 millimeters of mercury. I'm solving for volume. My moles I just solved for, 9.38 moles. The R value I'm going to pick is going to be 62.4 because this is millimeters of mercury. My temperature is 23.0 degrees Celsius, but I've got to add 273. So that's 296 Kelvin. So if I want volume, I can go ahead and then divide by 744. Help if you could see it, right? There you go. There it is. Okay, that's millimeters of mercury. So I've got 9.38 times 62.4 times 296 divided by 744. I'm getting a magical volume of, looks like I need 3 sig figs, 234 liters. All right, so that would be my answer. I've got another example problem right here. So if you want to go ahead and pause the video and give this one a shot, you can look at the answers there. All right, and here's the work for this problem. So this is the ideal gas law in stoichiometry.